In this lesson, I'm going to review the properties of open tubes that are resonating. Now, resonating open tubes have properties which are similar to strings, and you've already reviewed the lesson on strings which are resonating. So here I have sketches of the three harmonics of open tubes which are resonating. N is equal to 1 is the fundamental frequency, or the natural frequency. That's the minimum. So if you take a tube, an open-ended tube, and you strike it like a wind chime, or you blow air through it, what will happen is you will develop a wave pattern that consists of half of a wavelength. Now, what I've done on all of these diagrams is I've divided everything into quarters. 2 quarters make a half. And the reason I've done that is it's easier to visualize visualize and compare one harmonic to the next. Just as a reminder, here's a diagram of a sine wave, and you'll notice that a complete sine wave, a crest and a trough, is made up of 1, 2, 3, 4 quarters. That's one complete wave. So since there are 2 quarters here, there's only half a wavelength in this length of tube when it is vibrating at n is equal to 1, at its natural frequency. Now, if we look at the relationship between wavelength and the length of the tube, you see I have this as length is equal to 1/2 lambda, or the wavelength. And if we rewrite our this information in terms of frequency and speed, the frequency of the fundamental is equal to the speed of the wave divided by 2 times the length of the tube. And you'll notice that that is the exact same formula that you have for the fundamental frequency of a vibrating string. Now, when n is equal to 2, the second harmonic, that's also called the first overtone. In the second harmonic, we see that we have 1, 2, 3, 4 quarters. 4 quarters is 1 whole. So L is equal to lambda, and the frequency of the second harmonic is equal to V divided by L. And in the third harmonic, we have 1, 2, 3, 4, 5, 6, or 6 quarters, or 3.5 lambda. So the length of the tube is equivalent to 3.5 times the wavelength. Now, overall, we can summarize the frequency for any harmonic in terms of which harmonic we're looking at, as the frequency of any harmonic is equal to the harmonic number times the speed of the wave divided by 2 times the length. And you'll recall that that's the same formula that we use for strings.